we have so far have not allowed the fluid to flow. Okay, we have what's called fluid statics. But of course, a fluid can flow, and one of the most interesting things when it comes to fluid is watch what happens when the fluid flows. And when the fluid flows, we call it fluid dynamics. Okay. In general, the flow can be a complicated situation, but we're going to study a simple case, and that is we're going to restrict ourselves to a very simple kind of flow, which is called laminar, non-viscous, and irrotational flow. What is laminar flow? The term laminar here means steady. Okay, now what does that mean? Well, you know, if you follow a particle, okay, if you follow a particle in the fluid, it moves something like this, right? At one point it's here, the next moment it's there, it's there, it's there. We can try to follow this particle. Okay, but the problem with that is that this particle can move in a complicated manner because it's also being pushed around by the surrounding fluid. Instead of focusing on this particle, we can choose a different perspective. We don't follow a particular particle, rather we focus our attention on a particular location in the fluid. Let's say this location, okay? If you look at this location, say you have a camera, video camera trained at that location, okay? You find that, you know, at different moments, you know, different fluid particles will come in to pass that point, right? Let's say at one moment, a particle comes in, a fluid particle comes in, flows this way, right? What's a laminar flow? A laminar flow is a certain type of flow in which the flow pattern never changes over time, which means if you look at this particular region, particular point, any fluid particle passing through this point has exactly the same velocity. In other words, you take a video shot of a flow pattern. Okay, if you wait for another 20 minutes, you're not going to see something like that. Okay, because that would mean that 20 minutes later, another particle come to the same point, would have a different velocity. That is not a laminar flow. It's not a steady flow. Steady flow means the flow pattern never changes with time. Okay, so you know, at one moment you see particles flowing this way, the next moment you flow this way, next moment flow this way. It never changes. Okay, this is the flow line, and this flow line has a constant shape and size. It never changes over time. Now, this is what I mean by laminar flow. Okay, non-viscous. The term viscosity has to do with friction. Okay, non-viscous means different parts of the fluid do not rub against one another. If they do, that's going to cause heat to be generated, and that would mean that the mechanical energy is no longer conserved. We're not going to worry about it. Okay, in other words, we're not going to worry about glue. Okay, that of course is a very viscous flow. What about irrotational? Okay, in other words, there's no whirlpool. Okay, there's no whirlpool going on. There's no rotation like this. Okay, so we're looking at a laminar, non-viscous, and irrotational flow. If the flow is laminar, then if I follow a flow line, okay, you find this flow line never changes over time, right? And then let's look at a neighboring flow line, yet another one, and so on. Okay, you look at a whole bunch of flow lines. And let's imagine all these flow lines are very close to each other to form a certain tube. Okay, a tube. So we call this a tube of flow. This tube of flow is bordered by all these flow lines. Now, remember, the flow flows in a laminar fashion, which means no matter when you look at it, you will never see a particle of fluid going this way. Okay, because any particle that passes through this point will have to have the exact same velocity, which is this way. Okay, that means no particle of the fluid can actually cross the border of a tube of flow. Okay, so if a particle is originally inside a tube of flow, it keeps on going and never gets out. So that tells us the tube of flow can separate the flow into two regions. One is inside the tube of flow, one is the outside. Okay, particles inside and outside the tube of flow will never mix. Once you're outside, you never have a chance to go in. Once you're inside, you never have a chance to go out. and the shape and size of the tube of flow is controlled by the contour of each flow line, and that never changes. Okay, so the tube of flow is an interesting and convenient idea. We can use that to isolate certain fluid movement. Okay, let us take a look at what we can do when we apply the concept of tube of flow. Imagine a tube of flow like this. Okay, I didn't draw all the border lines, of course. It's cumbersome, but let me draw just two representative curves. Okay, so you have this tube of flow, right? Let us focus our attention in this region. Okay, here is a part of that tube of flow from point 1 to point 2. Okay, now particles will flow perpendicularly to the surface. Okay, here particles come in, here particles come out. I am going to assume at this point that the flow is also incompressible. Okay, what does that mean? It means the density cannot change. Okay, you cannot take the fluid and squeeze it. For example, water is nearly incompressible, so that is actually not a bad approximation in many cases. What does that mean? It means you cannot put more or less particles of fluid in this region. This region has, of course, a fixed volume, and since the density cannot change, the amount of mass that's contained within this region, within this part of the tube flow, will never change. But we know particles do go in and out because of the flow, and therefore we say that if you look at a certain period of time, delta t, if over here you got this much fluid coming in, and over there the same exact volume must come out. Okay, so this is the volume going in, this is the volume going out. They must equal to each other. Otherwise, the mass of the fluid inside between here and there will have to change. What can we learn from this observation? Well, let's look at a time dt. Okay, within a time dt, I want to know what is this volume. This is the volume of the fluid that actually can make its way into this gate 1. Okay, this gate 1 has an area A1. Okay, that's the cross-section area A1. The speed of the flow at this location is V1. Now, if a fluid particle want to make its way all into the gate within a time dt, it cannot be all the way there, right? That would be too far. It doesn't have a chance to make its way in. It must stay within this volume, and this height of the cylinder must be V1 dt. Why? Because if the speed of the particle is V1, then let's assume the particle is here at the edge. Okay, with the speed V1, it can barely make it to the door. Okay, because it covers the distance of V1 dt, right? So any particle within this red volume can actually make its way through gate 1 into this region. So what is the total volume of the particle going in? That will be the volume of this red region, which is cross-section or A1 times the height, which is V1 dt. Okay, again, the total volume between here and there is constant. Okay, so you got this much volume flowing in, a same amount of volume must have to flow out. Okay, how much water flows out? Well, similarly, that will be A2 V2 dt. V2 is the speed of the flow at that point, V2. Okay, the same over the same time interval dt. If you cross out that dt, what do you get? You get A1 V1 equals A2 V2. In other words, you pick up two arbitrary points, point 1 and point 2, along the same tube of flow, as long as it's along the same tube of flow. Then for any incompressible laminar flow, it turns out that A1 V1 equals A2 V2. Or, in general, the product of the cross-sectional area of the tube of flow times the speed at that location is equal to a constant. Okay. This is to ensure that the volume coming in at any location equals the volume coming out at a different location on the same tube of flow to ensure the incompressibility of the flow. And this equation is called the equation of continuity. We're going to use that a lot. Okay, this formula actually makes sense. What it basically says is that if you look at a very narrow region versus a very wide region, in order to sustain the same rate of influx, the water has to flow very fast, right? In order to rush through this narrow gate. And over here, you have a large area that water can flow out, so you don't have to flow that fast. You can slow down. So basically, the narrower the region, the faster the water will have to flow. Okay, you might think that doesn't quite make any sense because you probably realize when you drive on a freeway, when there's a bottleneck, this is the bottleneck, right? Isn't that where the lanes get narrower, speed up, do you? Okay, but this is just, here it says that in order to sustain the same rate of flow, when you go through a bottleneck with a narrower region, you actually have to pick up speed. How does that work? Well, we have to understand that in the freeway traffic, we're dealing with a compressible, not incompressible flow. So here's the deal. Suppose you have, traffic, right, like this, right? Here's a bottleneck. Okay, suppose something happens, okay, like an accident happens. Okay, then you got cars. Each car, we can think of it as a particle of water. It comes in, okay. It comes in, okay. It comes in and slows down, and slows down, and slows down. What happens is you're going to have a pileup of cars. You see, the number of cars actually can increase. Okay, so if you mimic the traffic flow, the traffic pattern as some sort of flow, it is certainly not an incompressible flow because cars can back up. You can actually have an increase in the number of cars. It is no longer an incompressible flow. Okay, so this is the equation of continuity. Now, one of the most important principles of fluid is called Bernoulli's Principle. It's named after Daniel Bernoulli. Consider a laminar flow, not laminar and non-viscous. Okay, it's laminar, therefore I can use a tube of flow to study it, and it's non-viscous, therefore we know the mechanical energy is conserved. Assume, a tube of flow starting from here and end up there. There's a certain amount of volume, okay, and this volume can never change. What we want to do is we want to study a certain amount of fluid, the fluid that's originally trapped between here and there. Let us follow this part of the fluid, see how it moves. Now, when you apply whatever conservation law, Newton's law, whatever, you must apply to a certain fixed amount of mass. You don't want to just say, okay, let me only focus my attention to the fluid between here and there because, the fluid comes and goes, right? You must therefore, this time, follow the fluid as it goes. At t equals 0, the fluid starts from here and ends up there. That is the part of the fluid that we study. Let's say the mass, is m. Okay. What happens a time dt later? All right. A time dt later, the fluid from here has moved to there, right? It has moved by how much? By v1 dt, right? Meanwhile, the fluid over there, the front edge of the fluid has moved there, right? What's that distance? That is v2 dt. Okay, what I want to know is what is the change in the kinetic energy of this fluid that flew from here to there over time dt. You have to understand that at any fixed location, any fluid particle going through any fixed location must have the same exact speed because that's a laminar flow, right? So if you compare the original fluid, which is from here to there, to the new configuration of fluid, which is from here to there, you find there is a common region between here and there, okay? Between here and there, the fluid particles may change, but they carry the same exact speed because of whatever particle it is, when it passes through that point, must have the same speed. So if you look at net change in the kinetic energy for this fluid going from here to there, what you need to realize is that all you have to do is to realize that, okay, you have this much extra coming out that you didn't have before, but you lost that much. You see? Everything in between. is the same. The kinetic energy did not change because the speed did not change. Okay, so what is the change in the kinetic energy then? Delta K equals this extra kinetic energy minus this old amount of kinetic energy, right? So we have 1/2 m v2 squared minus 1/2 m v1 squared. Let me use delta m. Okay, delta m. What's delta m? That is this mass here. Okay, it's the mass from here to there, which is equal to the mass from here to there because of the continuity equation, of course. The same amount of fluid must flow in and flow out. So this is the change in kinetic energy for this fluid, okay, trapped between here and there. Now, according to the work energy theorem, the change in kinetic energy comes at a price. What is it? It must equal to the net work done by all the forces, right? Okay, let's look at the forces that's doing work. Okay, first of all, there is a pressure from the surrounding fluid. That's P1. There is also pressure from the surrounding fluid here is P2. Now the flow is this way, so P1 does positive work and P2 is against direction motion, does negative work. So let's look at what this W is equal to. Okay, W is equal to positive work minus negative work. How much is the positive work? That is the force here times the displacement. The force is P1 A1. Okay, what's displacement from here to there? That's V1 dt1. Okay, over here, how much work is done from the pressure there against the direction of motion? That was negative P2 A2 V2 dt. Right? Okay, is that all? Well, don't forget there's also the gravitational effect, the gravitational force. So basically, gravity also did some work from here to there. You lost this much volume, again that much volume. Basically, gravity did negative work is from this drawing, you know, you have to lift yourself from lower position to higher position. Let's say these two regions differ in height by an amount h. Gravity did negative work because it's lifting from low to high. So minus the work done, plus the negative work done by gravity, that is delta m times g times h. Okay, times h. In fact, instead of h, let's do it this way. Let's assume that we have a ground level. Okay, an arbitrary ground level. This height is y1, and a new height is y2. And then, of course, h simply equals y2 minus y1. Okay. Okay, we have delta k, we have w. Delta k equals w. Right? Let us equate these two expressions, delta k and w. Let's see what we get. We can now write 1/2 delta m v2 squared minus 1/2 delta m v1 squared equals to what? Okay, P1 A1 V1 dt, right? Minus P2 A2 V2 dt, and then minus delta m times g, okay, times y2 minus y1. Alright, we got delta m. What's delta m again? That's the amount of mass that flows into the tube from point 1. It's also the amount of mass leaving the tube from point 2. Okay, but on the other hand, if you take a look at A1B1 dt1, what's A1B1 dt1 anyway? If I put the slide back momentarily, okay, this is A1, the cross-section area A1, V1 dt. Okay, so A1 times V1 dt, what's that? That is this little volume, isn't it? Okay, so that's this little volume, and what is the mass of this little volume? Isn't that delta V? Okay, so isn't that delta M? So therefore, in here, I have A1 B1 dt and I have delta m, right? If I divide everything by A1 V1 dt, that's just the volume of the mass delta m, right? So basically take delta m divided by its volume, what do you get? Don't you get the density of the fluid? Okay, so if I did that, then this first term becomes 1/2 rho V2 squared, right? Similarly, the second term, minus 1/2 rho V1 squared. Look at this side. P1, that's the only thing left for this term. What about the next term? P2. A2 V2 dt. What's A2 V2 dt? It is the volume gained at point 2. That equals the volume lost at point 1 due to the equation of continuity, right? So if you divide by A1 V1 dt for every term, it's the same as divided by A2 V2 dt. So this is gone. All right. So what's left? One last term. Delta m over the volume, and that's again rho. Okay. Rho g and then y2 minus y1. Okay, we're almost there. You got a term depending on point 2, point 1, point 1, point 2, point 2, point 1. It's a mess. What I want to do is I want to move all the terms belonging to point 1 on one side, move all the terms belonging to point 2 to the other side. And let's see what we get. Okay, you move this guy to that side, that is 1/2 rho V1 squared, okay, to that side. And there's a P1, of course, P1. What else? There is a negative rho g times negative y1, so that's plus rho g y1. Okay, those are the three terms that depend on point 1. There are three similar terms depending on point 2. In fact, you move this guy over there, that's P2. Okay. There's already 1/2 rho V2 squared. There's another term, rho gy2. It's a negative sign. Move it to the other side, positive side. Rho gy2. Okay, so you see the sum of these three terms, P1, 1/2 rho V1 squared and rho gy1, equals to the sum of three similar terms, P2, 1/2 rho V2 squared, rho gy2. Okay, point 1 and point 2, these are two arbitrary points along the same tubal flow. So what does that tell us? It tells us that anywhere along the same tubal flow, the sum of these three terms must be a constant. So P plus 1/2 rho V squared plus rho gy equals a constant along the same tube of flow. That is what's called Bernoulli's principle or Bernoulli's equation. It has many, many applications. Okay. If we take a good look at it, you'll find that along the same tubal flow, suppose for the time being, let's say, y, which is the height, is the same. Okay, look at 2 points. They have pretty much the same height, so this term is the same. They're on the same tubal flow, so the sum of these three terms must be equal. Since the last term is a constant, the sum of these two must be equal. What does that tell us? It tells us that if a fluid flows past a faster region, a narrower region, so it flows faster, so V is greater, what happens to pressure? It must be lower. Okay, so to put it in a short version, pretty much the higher the pressure, the higher the flow speed, the lower the pressure. This is an interesting observation we get from the Bernoulli's principle.